Okay, so welcome back for section 5.3, part 2. We're going to continue on finding some values of definite integrals using some area formulas from geometry. And we're working on this one right here. Okay. Now, in order to see the geometry, I'm going to make a quick sketch of it. So my function f of x, my integrand, is the function x plus 2. So I'm going to make a quick sketch of that on the interval from 0 to 3. X plus 2 is a line with a slope of 1 and a y-intercept of 2. We are evaluating it from left hand endpoint 0, right hand endpoint 3. The function is non-negative, positive on that entire interval. So that's going to be the area. Now, if you look at that, you'll see that that's a trapezoid. You might have to turn your head sideways to see it. But this will be our base 1. This will be our base 2. This will be our height. Then the area of that trapezoid is base 1 plus base 2 times height divided by 2. Our base 1 is the y value of that left-hand edge. So it's right there. That's, 2? Our base 2 is the y value here. So it's the y value when x is 3. So that's 5. Our height is this length, which is 3, divided by 2. 5 plus 2 is 7, so we got 21 halves. So then the definite integral from 0 to 3 of x plus 2 dx is equal to 21 halves. All right, moving right along. We got, what is this? This is, wow, what's going on here? Now, depending on how good your algebra is, you might recognize that the integrand is the top half of a circle. Top half of a circle with a radius of 3. Well, if the area formula for a circle is pi r squared, then the area formula for a semicircle is going to be pi r squared over 2. Or pi times 3 squared divided by 2, 9 pi over 2. So the integral from negative 3, positive 3, the root of 9 minus x squared dx is 9 pi divided by 2. Now, if you're wondering about the algebra of that, if y equals the square root of 9 minus x squared, then y squared squaring both sides, move the x squared over, circle, top half of the circle. If you wanted the bottom half, you just take the negative root. Okay. All right, one thing to note about integration, whether it's being a definite integral or an indefinite integral, but definitely in the definite integral, no pun intended, the variable is sometimes referred to as a dummy variable. Because you'll notice that the answer is a number. The answer doesn't contain a variable. The variable doesn't matter. So these two integrals have the same value because the variable doesn't matter. So if x plus 2 is 21 halves, then t plus 2 would also be 21 halves on the same intervals. Okay? It doesn't matter what variable you use. We usually use x's because then it relates back to all the graphing that you have familiarity with. But there's nothing about it that requires that. All right, so properties of definite integrals. The first property of definite integral says that if f is defined on the interval, wait, that's not an interval. That just simply says if your function is defined at a single value, then the integral from that single value to that single value is 0. Okay. Let's see if we can make some sense of this. That's my integral. And the value of that integral is 0? Why? Well, if we think of this in terms of the area problem, to have area, you have to have width and height. And this has no width. So if the interval isn't an interval, it's just a point, the value of the integral is 0. That one's unique and it's interesting, but it's not as useful as one would think. The second one is useful. The second one says, find a function that's integratable, that's integrable, on an interval. What happens if you flip the limits of integration? Because this interval says a is on the left, b is on the right, and we're integrating in this direction, going from a to b. When I go from a to b, all my delta x's are going to be positive numbers. All my delta x's will be greater than 0. But if I do this, suddenly I've flipped my limits of integration. So now I'm not moving from a to b, I'm moving from b to a. And now all my delta x's are going to be a negative number. All my delta x's will be less than 0. And so when I do that Riemann sum that's hidden inside of these integrals, if the delta x's are all negative, then the value of that integral is going to be the exact same, but the opposite, exact same numerical value, but the opposite sign as the integral from a to b. All of the heights will be the same, just since the direction of travel changed, we chuck a negative in. Okay? And this is useful because this gives us a way to change our limits of integration, to flip them if we ever need to. So if there's some simplification that could exist by flipping those limits of integration, we're allowed to. We just have to remember that the value of our integral is now the opposite, the negative, of what it started out to be. Okay, the additive interval property. Find a function f that is an integrable on the intervals formed by a, b, and c, then a to b is a to c plus b to c. And I have a figure for you here. A to c we're going to call the left, c to b we're going to call the right, and we are going to say that left plus right is equal to the whole thing. Or that the integral from a to c of some function f dx plus the integral from c to b, the right one, of some function f dx is just the integral from a to c of f of x dx, the whole thing. Now I want you to be careful about something though. While this picture and this language over here forces c to be in between a and b, there's nothing about the definition that requires that. Okay? If your picture was somehow an interval where here was a, here was b, and here was c, well then the whole thing is from a to c. And then the left piece, oops, wrong color. The left piece would be, wait, I got that backwards. Let's start this one over. Why won't this erase? Okay. A to B, just be this piece, the whole thing. A to C would be all of this, And then here's the tricky one. C to B would be this piece, but going backwards. And because it's going backwards, it'd be negative. So then the yellow minus the pink would give you the green. Right? But we rarely see that application of it. We almost always see this application. Whoop, I don't want the arrow. This application right here, where it's A to C, C to B, whole thing, A to B. And I just realized there's a typo right here. The whole thing is A to B. Silly me. All right, let's see if we can make this work. Let's see. My job is to take an integral from 0 to 10 that's worth 17, take the same integrand from 0 to 8, know that it's worth 12, and find the value from 8 to 10. Well, if I think of this as like a number line, here's 0, here's 10, and then I got 8 here. So the whole thing is worth 17. Zero to 8 is worth 12. So what's 8 to 10 got to be worth? Well, then 8 to 10 must be worth 5, so I can take 12 plus 5 to get my 17. Or, if you want to see it mathematically, the integral from 0 to 10 of the function f of x dx is going to be equal to the integral from 0 to 8 of the same function f of x dx plus the integral from 8 to 10 of the function f of x dx. 17 equals 12 plus I don't know. Solve, get y equals 5, or more precisely, the integral from 8 to 10 of f of x dx is equal to 5. Okay? Some more properties of definite integrals. Now, these are nothing new. If you look at this, this looks exactly like the indefinite integral property. The indefinite integral property said the integral of k times f of x dx was equal to k times the integral of f of x dx. What's changed? Well, we added limits of integration. We took an indefinite integral and made it a definite integral, but the math is still the same. It says if you got a coefficient and you don't want it in there, take that coefficient and pull it out. What's the second one say? It says if you have one integral and your integrand is the sum or difference, you can rewrite that as two integrals, the sum or difference. Okay? The only thing you got to be careful of is that your a, your b stays the same everywhere you go. This is also just like the indefinite integral. The indefinite integral said the indefinite integral of f plus or minus g dx was just the integral of f dx plus or minus the integral g dx. We've just added limits of integration. All right, example for this. My job is to evaluate this integral, the integral from 1 to 3 of negative x squared plus 4x minus 3 dx, by knowing the integral of x squared is 26/3, the integral of x is 4, and the integral of dx is 2. Now, this is one of those situations here where I wish we were better with math. I wish we wrote this. The integral of 1 times dx is 2. And somehow I'm supposed to use those three things to find the value of this integral. So I'm going to use properties of integrals to tear this thing apart at the addition and subtraction. I'm going to use properties of integrals to remove coefficients and rewrite that integral, that one definite integral, as 3 definite integrals. And now, this will get replaced with 26/3, this will get replaced with 4, and this will get replaced with 2. The value of those integrals. The negative stays, so I've got negative 26/3 plus 4 times 4, okay, that's that 4, that's the value of the integral, minus 3 times 2. I've got negative 26/3 plus 16 minus 6, that's 10, so 4/3 when it's all said and done. So the value of the integral, the value of the definite integral from 1 to 3 of the integrand negative x squared plus 4x minus 3 dx is 4/3. Okay. The preservation of inequality, our last property, and the end of section 5.3. You ready? You've got a function f. It's integrable, and it's not negative on an interval. Well, if the function never goes negative, the integral can't be negative. If the function never goes below the x-axis, the value of the integral can never be smaller than 0. Right? Now, non-negative is one of those tricky phrases that we use. Non-negative means it could be 0, or it could be positive. It just can't be negative, which is why the value of the integral still could be 0. Right? That one's good, that one's important, but the second one is better. The second one says, if you got two functions, f of x and g of x, they're integrable on an interval a to b, and f of x is always smaller than or equal to g of x, then the integral for f of x better be smaller than or equal to the integral for g of x. Okay? The integral from a to b of f of x dx is that green piece down there. The integral of g of x is the green piece plus the blue piece, because it's bigger than f of x for that entire interval. And since it's bigger than, okay, the value of the integral better be bigger than. Okay? There's something else there's something else though that's hidden in here, that isn't stated but's hidden in here. If I told you that this green piece down here had an area of 6, and if I told you that the whole thing had an area of 10, what's the area of the blue piece? Well, it'd have to be 4, so that 6 plus 4 could add up to 10. So that's hidden in that definition. It's not really stated. You'll see a bunch more of that in Calc 2. Okay? But it's hidden in there, so keep that in mind. Top minus bottom equals difference. Right. All right, this brings us to the end of section 5.3. Review really quickly, because 5.3 is a big one. 5.3, we took a look at the idea of a Riemann sum. All a Riemann sum was the area problems from section 5.2, but we said the function doesn't have to be positive. It could be above the x-axis, or it could be below the x-axis. Divide it up. Find a bunch of heights, and I'm putting that in quotes because it doesn't have to be positive, so it really isn't heights. Find a bunch of widths, multiply heights times widths, add them up, you got the value of the integral. If you use infinitely many, it ceases to be an approximation and becomes the exact value. This is our shorthand notation for finding that exact value. It's called the definite integral. It has three important parts: the integrand, the lower limit of integration, the upper limit of integration. The lower limit is the left-hand edge, the upper limit is the right-hand edge, and the integrand is our function. We got rid of the need for positive functions, and we said all it has to do is be continuous. And then we found a bunch of integral values. Okay. We said if you're not negative, then the value of the definite integral is the area that we were finding in section 5.2. Did some examples where geometry worked. Okay. Then we took a look at properties. If the integral doesn't go anywhere, its value is 0. If you flip the limits of integration, just add in a negative. If you break it apart into a left and a right, a left plus a right is the whole thing. If you have a coefficient that you don't like, pull it out. If you have addition that's causing you trouble, rip it apart. If f never goes negative, the integral can't be negative. If g is bigger than f, the integral for g better be bigger than f. And that brings us to the end of section 5.3.